Welcome to How AI Models Work.
Glad to be here for this.
So imagine you are listening to someone on the phone. They take a deep breath, they let out this heavy sigh, and they sound like genuinely heartbroken.
Right, a very human moment.
Exactly. But now imagine that the speaker on the other end is actually just a complex string of mathematical equations.
Yeah.
It has never physically breathed, and it's never felt a single moment of sadness in its entire existence.
It's just math.
Yeah. So if you are joining us for this July 2026 guide, we are on a mission today to answer a really vital question. When you hear a completely natural AI voice or, see a flawless AI image, what actually created that result?
And importantly, what does it actually establish?
Right.
Because the recurring lesson we're going to see today is that a polished, natural, or convincing AI output does not by itself prove reliability.
Yeah, the output looks and sounds totally finished to us, but there is this whole hidden architecture underneath it.
Exactly. We have to look at the mechanics of that architecture. We're going to trace how AI processes voice and images, look at the hidden variables and system choices.
Biases and stuff.
Right. And then examine the training loop and finally explore how scientists actually use these models for real-world validation.
So let's just jump right into it. Let's start with the voice, since that's, the most human-seeming output.
It sounds incredibly natural, but it is just a chain of mathematical predictions.
It's not like a recording pulling from a massive library of human sounds.
No, not at all. When a text-to-speech system is handed a sentence, that plain written text doesn't have a complete performance script.
Right, it's just words on a screen.
Exactly. It doesn't tell a system how long a pause should be or where the pitch should rise for a question.
Or where to take a breath.
Yeah. The model actually has to invent all of that timing and prosody. The rhythm, the pitch, the emphasis.
It's kind of like giving a script to an actor, right? The script just has the dialogue, but the performer has to invent all the stage directions.
That's a great way to put it.
They decide on the dramatic pauses and the pitch shifts. But let me pause and challenge something here. If the voice sounds incredibly sad or really excited, is the system experiencing that emotion on any level at all?
No. Realistic speech comes purely from learned acoustic patterns.
Okay.
The system does not feel emotion. It is not physically experiencing the act of speaking.
Right, no lungs, no vocal cords.
Exactly. It has just learned from training data that certain text combinations correlate with specific mathematical audio patterns.
So how does it mechanically do that? How does it turn text into audio?
Well, one common architecture involves creating an acoustic representation first, often using something called a Mel spectrogram.
A Mel spectrogram.
Yeah, you can think of it as a visual map of sound. It maps out how sound energy is distributed across different frequencies over time.
Okay, so it builds this visual map first.
Right. And once that map is generated, a separate component called a vocoder converts that spectrogram into the actual audio waveform.
The actual sound we hear.
Exactly. Though I should note, not every modern voice system uses this exact architecture today.
Oh, really?
Yeah, some generate audio tokens or waveforms differently, but the underlying principle of predicting acoustic features remains the same.
Got it. But what about when we talk back? Like, the pausing and interrupting in a normal conversation, how does the AI know when you are actually done speaking?
That's endpointing.
Because if it just uses a simple silence threshold, that's incredibly awkward. Like, if I stop to think for 1 second.
It just jumps right over you.
Okay.
Yeah. A simple silence threshold is only the most basic method.
Right.
More advanced systems combine multiple signals to estimate whether a speaker is finished. They look at acoustic clues like the pitch of your voice dropping.
Or breathing.
Yes, the sounds of an intake of breath.
Mm.
But they also look at linguistic and learned signals.
Wait, linguistic signals?
Yeah. If you say, the 3 reasons I called are, and then you pause for 2 seconds.
It knows I'm not done.
Exactly. It calculates that the sentence is grammatically incomplete. It uses that linguistic context to wait, rather than cutting you off.
Oh, wow. Okay, so voice AI is matching acoustic patterns without feeling them. Let's pivot to image AI, because a similar dynamic happens there, right?
Very similar, yeah.
Image AI matches visual patterns without actually experiencing the physical world.
Right. Visual models process information very differently than human eyes do.
How so?
Well, they don't look at a photograph as one complete, continuous scene. Instead, they process images by chopping them into numerical representations.
Like slicing it up.
Yeah, many vision models divide the image into a grid of small square image patches. And then they convert those patches into visual tokens.
Which are just numbers.
Exactly, sequences of numbers.
So it takes a picture, slices it into a grid, and turns those little squares into numbers, almost like words in a sentence.
That's a good analogy.
But just because it can recognize those pieces doesn't mean it actually grasps what's happening in the picture.
No, not at all. There is a big difference between recognizing objects and understanding a scene.
Like, an AI can identify the visual pattern of a cat. It can spot a conference table and people in business suits.
Right, it can label those pixels.
But it completely misses the joke of an image showing cats running a corporate board meeting.
Exactly. Identifying a cat or a chair is fundamentally a localization and classification task.
Sure.
It's just calculating that specific pixel arrangements equal the label cat.
But understanding the humor.
Understanding the humor, the absurdity, or the social context of cats in a boardroom that requires inference about human expectations. The model recognizes the objects, but it does not possess an understanding of the scene's actual meaning.
Okay, so let's talk about how the model relates these concepts to each other. I often hear the term latent space.
Yes, latent space.
People describe it as a map where concepts live. But let me push back on that map analogy. If it's a map, does that mean a concept like cat has literal fixed coordinates inside the computer?
No, definitely not. Latent space is a learned numerical representation. Maps and distances are just teaching analogies.
Okay.
We use them to visualize something operating in hundreds or thousands of dimensions. Concepts do not have fixed, permanent coordinates.
So if a model generates a cat-dog hybrid, it's not just calculating the exact geographical midpoint between those two fixed points.
No. The model relies on really complex statistical relationships across many dimensions, not a static 2D map with pushpins in it.
That makes sense. What about when engineers try to look under the hood? They use these things called AI heat maps, right?
Yeah, heat maps are common, but they can be an illusion if you assume they work like human attention.
Because they just show which input regions influenced a prediction. They don't reveal thoughts or human-like reasoning.
Exactly. A heat map just highlights the mathematical weights that drove an output.
Give me an example of that.
Well, say a model predicts an animal in a photo is a wolf. The heat map might show that it was heavily influenced by the background pixels, specifically the snow behind the animal.
Wait, it used the snow to identify the wolf.
Yeah. If most wolf images in the training data featured snow, the system learns a predictive shortcut. The presence of snow becomes a reliable mathematical indicator for the label wolf.
Wow.
The heat map highlights the snow, which just illustrates that predictive shortcut. It does not mean the model was applying human reasoning to look at the animal's fur or snout.
Those predictive shortcuts are fascinating for a photo of a wolf, but they take on a totally different weight when we apply these systems to society.
Absolutely.
Because those shortcuts create uneven outcomes in systems making real-world decisions.
Yeah, and those uneven outcomes can emerge from almost every layer of a system's development.
From the data itself.
From the historical data collected, the labels applied, the measurement quality, proxy variables, the objectives set for the model.
The thresholds chosen for operation.
Exactly. Even the evaluation metrics and the final deployment choices.
Let's walk through a concrete scenario to see how those uneven outcomes hide in the math.
Okay, sure.
Let's say a company builds a model to review job applications, and they proudly state, our model is totally fair because we removed race, gender, and age from the data. It never even saw them.
Right, the blind defense.
Yeah. Why is removing those demographic columns an incomplete defense against bias?
Because removing those columns does not remove the correlated information that's still hiding in the rest of the data.
The statistical shadow.
Exactly. Features like a person's location, their vocabulary, or their employment history, they can act as partial proxies for the demographics you removed.
So the model still figures it out.
Well, the machine learning system calculates patterns across hundreds of these seemingly innocent variables. And in doing so, it can inadvertently reconstruct the exact information you thought you excluded.
Because it's relying on those proxy variables since they mathematically correlate with historical outcomes.
Yes.
But couldn't we just fix that by feeding the model more diverse data? Like just balance the data set?
Including more diverse data is important, definitely. But it does not automatically guarantee equal quality, coverage, or subgroup reliability.
Why not?
Because, for example, you might have equal representation of two groups, but the measurements for one group might be significantly noisier or less accurate.
Oh, I see.
Plus, different mathematical measures of fairness can actually conflict with one another under some conditions.
Wait, really? They conflict?
Yeah. You might have a definition of fairness demanding equal representation, and another demanding equal accuracy across groups, and the math might force you to trade one for the other.
So you can't just flip a switch to optimize all of them perfectly at the same time.
No, you can't.
To understand why these proxy variables and shadows get so deeply embedded, we really have to look at the engine where they are built, which is the training process.
Right. And training isn't just a one-time magical event.
It's a repeated loop.
A mechanical loop, yeah. The system constantly loops through four main steps. It processes examples, it makes predictions, it calculates its error, which is called loss, and then it slightly adjusts its parameters.
Let's drill down into calculating that loss, specifically for language models.
Okay.
Because when people hear loss, I think they imagine a simple measurement, like calculating the alphabetical distance between two words. But it's not just checking a dictionary, is it?
No, for language models, loss involves probability distributions. The model assigns predicted probabilities across its entire vocabulary for what the next token should be.
Okay.
When it calculates loss, those predicted probabilities are compared with the actual target token from the training data.
So it's not the physical distance between words.
Right. It's evaluating how much mathematical probability it assigned to the correct token and how much it wasted on incorrect ones.
So it's constantly adjusting millions of parameters to get those probability distributions tighter. But this brings up a huge issue with how we evaluate these systems. Say the engineers see a steadily falling training loss, and the model gets a strong average score on a benchmark test.
Right.
Does that mean the model is definitively reliable and ready to go?
Absolutely not. A falling training loss or a strong average benchmark score does not guarantee reliable performance on new situations, edge cases, or every specific subgroup.
Because it's just an average.
Yes. An average score tells you how the model performed across a broad aggregate. It hides the specific areas where the model might fail completely.
Which means there is no universal technical moment when a model becomes definitively ready.
No magical green light on the server rack, no.
Release relies heavily on human choice then.
Entirely. It depends on testing, the intended use case, knowing the specific limitations, and deciding what level of risk is acceptable.
And the system you interact with isn't even just the raw model that came out of that training loop, right?
No, it's constructed in distinct layers.
Okay, walk me through the layers.
The initial training loop creates a base model, which basically just predicts the next token.
Right.
Then, post-training techniques shape its learned behavior so it can follow instructions safely.
And then the interface.
Yeah. System instructions, tools, filters, and user interfaces. Those are additional product layers.
That distinction between the base model and the product layers is so important. The polished interface is really just the final layer painted over this complex engine.
Exactly.
So if we know that average benchmarks hide edge cases and that models rely on predictive shortcuts, how are scientists relying on AI for high-stakes discoveries like drug development or climate modeling?
Well, in scientific AI, researchers use the models to identify patterns and narrow vast search spaces.
Narrowing the search space. Okay.
Yeah. If you're developing a new drug, you're dealing with millions of possible molecular structures. An AI model can process that to predict molecular structures or rank candidates.
So it accelerates selected calculations to point researchers in the right direction. It's kind of like a highly advanced metal detector. It can scan a massive field and tell a scientist exactly where to dig. But a beep from a metal detector isn't the treasure itself.
No, it's not.
You still have to get a shovel, dig the hole, and prove the treasure is actually there.
I love that analogy. A useful prediction is not the same as proof, causality, or established scientific evidence.
And we see this in climate science too, right? With surrogate models.
Yes, surrogate models are a great example.
How does a surrogate model differ from the traditional physics-based simulations that climate scientists use?
A physics-based simulation explicitly applies physical equations to calculate complex dynamics, like ocean fluid flow.
Which takes massive computing power.
Massive. But a learned surrogate model approximates selected calculations from examples or simulation outputs. It basically learns the patterns of the massive simulation to generate answers much faster.
But they are both ultimately just models.
Yes. Both are models. We should never call a physics-based simulation perfectly accurate either.
Because the surrogate is just approximating calculations based on patterns, it doesn't replace the entire climate model or the scientific process?
No, it doesn't. Outside of familiar training conditions, a surrogate model's predictions may become less reliable.
So it just breaks down?
Not necessarily. It doesn't mean it categorically cannot extrapolate or that it must automatically fail.
Right.
but it means that physical constraints, experiments, real-world validation, and expert judgment remain necessary. It accelerates the search, but it doesn't replace the science.
So as we move through all these different layers today, from voice generation to climate surrogates, we continually return to the core framework of our July 2026 guide.
Yes.
When you encounter a result produced by a model, you really have to ask, what produced this result? What was actually tested to verify it?
And what evidence is still needed before trusting it for a real-world task?
Right. Whether a model is generating vocal rhythm without feeling emotion, or finding a visual shortcut in the background of an image.
Or reproducing a statistical shadow bias, or predicting a new drug molecule.
Yeah, the output you see is only ever a starting point. So we invite you to explore the rest of the July 2026 guide for a deeper understanding of these mechanics.
Do not judge an AI system only by how polished, natural, or convincing its output appears. Ask what produced the result, what was actually tested, and what evidence would be needed to trust it for the real task.
HowAIModelsWork.com